Hello, everyone. So I will talk about the second program next spring. These are the list of the 5 co-organizers. And I want to draw your attention to the fact that out of the 5, 3 are in Europe. And in fact, in the previous program, I think we had out of the 5, 2 were in Europe. And that's an important feature that I'll come back to. So I want to start by telling you what I would call a tale of 2 volumes. So about 25 years ago, MIT Press published something, a handbook of theoretical computer science edited by Jan van Leuven. And it had 2 volumes. Volume A was roughly, I describe it, the theory of algorithms. So it was algorithm and complexity theory. And volume B is the more focused on programs and system, concurrency, semantics, and the like. It turns out that for more complex reasons that I have time to go into details now, the North American focus is mostly on volume A. That also means that traditionally most of the activities of the Salomon Institute are focused on volume A. And here there was a particular effort to broaden the scope and bring in volume B. And it means a heavier European presence, which given that we're going to be virtual in the spring is going to be a major challenge because of the time difference, let's say, between the West Coast and Central Europe. So what is the main theme of when we talk about theoretical foundation of computer systems? When you develop algorithms, then you want to know, does the algorithm do what it's supposed to do, and what is the complexity of the algorithm? When we build system and we write program, we build system, we have some what we call designer intent. The designer has some functionality in mind. And we want to know that the system that we build meet the designer intent. So this is, does what we have built, is it correct? This is a nutshell, is it correct? Now, of course, you can ask, what is designer intent? Intent is always an ambiguous thing. What's in your head? What's the intent? So people usually put things down in writing. But if you have seen, I would say, traditional requirement documents, they're written in natural language, and they are vague and ambiguous. So a proposal has been made many years ago to try to have formal requirement, to try to have more formal list of properties that the system is supposed to satisfy, and to use logic as a declarative specification language, because logic offers us precise syntax and semantics. I would say is the biggest success of logic, of first order logic in this case, has been SQL, which is based on first order logic. So Ted Code proposed using essentially first order logic as a query language for databases. And today this is industry, I think, approaching $50 billion a year. So this was a major success. Of course, Boolean logic we use for circuit design. And there are other logic that have been, for example, logic such as called PSL, property specification language, the system Verilog assertion, SVA, the IEEE standards that are based on temporal logic. So this idea of using logic as a declarative the specification formalism has had quite a lot of success. So how do we, so again, the driving question for the theory of system, how can we ensure that the system we build meet designer intent? And now designer intent is written to us in some logic, in a declarative formalism. And to simplify things, you can think of 3 answers. One is using theorem proving techniques to prove correctness. This is expensive, but it's the biggest hammer you can have. And it is used by companies such as Microsoft, and AWS is using it, invested quite heavily in this. The other approach is algorithmic verification. And here we use Facebook and Google and Microsoft in EDA tools use algorithmic verification. And the final thing is algorithmic synthesis. We go directly from the declarative formalism to the system we build. And this is less used in industry, but it's used in academic tools. So the important ideas here is one is to use logic for formal requirements, but the other one is logic is a high-level language, and automata is a low-level language. Its states transition very, very low level. And the crux is a connection has been established going back all the way to the 50s between logic and automata. between a high-level formalism,
1 minute.
which is logic, and low-level formalism. So the year is going to be, the program is going to explore several themes of TFCS. One is the connection between logic and automata. Again, the dichotomy between deterministic behavior and probabilistic behavior, worst case behavior essentially versus expected time behavior. Looking at system and their environments as adversarial games. If they are multi-agent systems, again, we look at games, we look at equilibria, and going from discrete behavior to analog behavior, dealing with real time and energy consumption. And the common theme is the combination of reasoning and automation, automated reasoning. And there is a synergy with the first program that Antonina talked about, satisfiability, also looks at automation of reasoning. And so the two programs have quite a lot of overlap. Thank you.